So we're going to do a few examples looking at conduction and that kind of big ugly equation that I showed you in the previous video. First problem we're going to look at is just heat being conducted up a metal rod. So if we've got a marshmallow roasting stick and we leave it in the campfire, if the fire is at 500, the air outside is 30 degrees, at what rate does heat flow down the 65 centimeter long rod with a radius of 0.5 centimeters. So rate of heat flow, that rate is something divided by time, right? Heat flow is Q, so we are solving for Q over T. Our equation was Ka over L times T1 minus T2. Okay, so if we start plugging in what we know, the value of K isn't given here, but it tells us that it's steel, so we can go look that up on a table. The K value for steel is going to be 40. And then we want the area here. Well, if this is a rod, the area is going to be the area of the end of this, so that's going to be pi r squared. So times pi, and we want the radius in meters, so that's 0.005 squared. And then we've got our temperature difference, so we're going to do 500 minus 30. It doesn't really matter which one is T1 and T2. All it's going to do is switch a positive and negative sign. And you should be able to keep track of which way the energy is flowing anyway by knowing that it flows from hot to cold. Okay, then we got to divide by the length of the rod, 0.65 meters. And that's really all there is to this problem. Throw all of this junk into your calculator and you get 2.27 joules per second, or watts if you prefer. So not a whole lot of conduction going from one end of the rod to the other. Part of that's because the rod is quite long and fairly small. Alright, let's look at a little more complicated example. Here we have a copper rod and an aluminum rod, same length, same area, attached end to end. So we have something like this where we've got two metal rods that are joined for whatever reason, who knows. This guy on this side is copper and this guy is aluminum. And we've got the copper guy in a furnace at 350 degrees Celsius and the aluminum side in an ice bath at 0 degrees Celsius. We want to know the temperature right here in the middle. Alright, so if we think about the heat flow, heat is going to be flowing down the rod in this direction. And heat flow has to be the same at any point during the rod. The reason we know that is because if at any point more heat is coming in than is going out, that little section will just get hotter and hotter and hotter and hotter. And that can't happen. So even at the junction here, heat flow is constant. So that means we can say the heat flowing through the entire length of the copper rod equals the heat flowing through the entire length of the aluminum rod. Now our heat flow equation is Q over T. So if we apply that to the copper side, that equals Q over T applied to the aluminum side. And then we're going to plug in our big fat Ka delta T over L equation. So T2 minus T1 over L equals Ka T2 minus T1 over L. Now we have to be careful. All of this stuff applies to the copper side. All of this stuff applies to the aluminum side. So the areas, though, we said they're the exact same size rod, so the areas cancel out and the lengths cancel out. But these K's are different and these T's are different. So K for the copper side is 350. Oops, no it's not. Where's my eraser? That's the temperature. You'd have to look this up on a table, and let me see, I think I've got that here. Yeah, K is 380 for copper. The temperature is 350 minus the temperature in the middle. I don't know what that is. That's our unknown. Over here we've got K for aluminum, which is 200. And then in this case the higher temperature is the one in the middle, so I'm going to call that guy T, same as this T, minus the lower temperature, which is going to be 0. So there is the physics. Now we've got a bit of algebra left to do to clean this up. So if we distribute this, 380 times 350 is 133,000 minus 380t, got my 0 in there, equals 200t, and then there's a 0, so that just goes away. If we move up over here, we got 133,000. I'm going to add 380 to both sides, so this becomes 580t. Then I divide both sides by 580, and we get a temperature in the middle of 229 degrees Celsius. So there you go. In case you ever find yourself in this situation, now you'll know what to do. Alright, I'm going to do one more example. You can actually stop the video here unless you want to see something that's going to help you on the bonus question on your next homework assignment. So here is yet more complicated situation. If we have a couple of layers of different materials, and this time we're not going to have them the same the same thickness, and we'll say that it's hot out here and cold over here, so that means we're going to have heat flowing this way. We'll just call this L1 and this L2. The areas are going to be equal, so they have some area there. We'll call temperature on the hot side T2 and this guy T1, and the one in the middle we'll just call TM for the one in the middle. Okay, and these are different materials. We're just going to do this in general, so I'll say this has some K value K1 and this has some K value K2. And if I want to find the rate of heat flow in terms of these variables here, in terms of the temperatures and lengths, then I can set up that same equation. I've got Q over T of the, I'll call this, this is just material 1 and material 2, right? So Q over T of material 1 equals Q over T of material 2 by the same argument that we used with those two attached rods. And now I'm going to do something a little bit different. So I'm going to say Q over T, because there is only one, is equal to K1 times A over L1 times, now the hot temperature for the first object is going to be this Tm here, so I'm going to have Tm minus T1. Okay, and then I'm going to have, I'm just going to leave it at that, and I'm going to say equals K2 times A over L2, and here the hot temperature is T2 minus the cold temperature is Tm. So rather than just setting these guys equal to each other and solving for something, that would allow me to solve for one of the temperatures possibly, but it's not going to get me Q over T. I guess I could solve for the temperature first and then come back and plug it in. But another way we can do this is I can make two equations out of this. I can set this equal to this stuff, and I can set it equal to that stuff. So I've got Q over T equals K1A over L1 times Tm minus T1, and I've got Q over T equals K2A over L2 T2 minus Tm. Next thing we're going to do is divide the Ka over L thing to the other side. So we're going to end up with Q over T times L over K1A, L1, equals Tm minus T1. And then we're going to have Q over T times L2 over K2A equals T2 minus Tm. And then the next thing we're going to do is we're going to add these two equations together. So I'm going to come up over here. I'm going to have Q over T, and then I can factor that out because it's going to be in each of these terms. So I'm going to have L1 K1 times A plus L2 K2 times A, and then adding the other sides we're going to have Tm minus T1 plus T2 minus Tm You'll notice these TM's go away. We can also factor out an A, and we rearrange everything once again, and we end up with, come on pen, Q over T equals A times T1 minus T2 over L1 over K1 plus L2 over K2. And so here's our big nasty equation where we can get the heat flow through kind of a sandwich of a couple of materials. And if you remember in the first video, I also mentioned that R, which is the value for like the thermal resistance value when you're buying insulation and whatnot, that's defined as L over K. So we could actually replace this denominator here, and we can say A times T1 minus T2 divided by R1 plus R2. Alright, now we're not going to use this a lot, but there will be a bonus question where this will come in handy. Okay, see you next time.